So Jai Hind everyone. So this is the second lecture of the after this previous lecture IPv4 and IPv6 header datagram. So in the previous lecture we have studied that what is the header format of IPv4 and also did some practical or numerical questions on this IPv4 header datagram. So today we will resume after this. So we have studied in the previous lecture about maximum transfer unit. So this is the maximum transfer unit of the data size. What size of data we can deliver from source to destination. Okay. So this is depend on the different protocols that if we are using token ring with 4 Mbps, then we are delivering 4464 MTU, 4464 bytes of MTU. If we are using FDDI, then 4352. In the similar way, if we are using Ethernet on the local internet, then we are transferring 1500 bytes of data from source to destination. Okay. So this we have discussed in very fast way. So today we have some time, so we can discuss it very slowly. So in the next field, this is your do not fragment, more fragment, and the one bit is unused. So this is your do not fragment and more fragment. If do not fragment is 1, so what does it mean? It means the frame do not have any further fragments of this packet. If M is 1, then it means there is further fragments of this current packet. Okay. So there are some, this is the example of fragment offset. So fragmentation. So this is the offset. We have to divide the starting number of this offset divided by 8, because 1 byte is equals to 8 bits. So we have to divide it by 8, and the total size of this offset is 440000023999. This size is given in example, given in a question, so that you can very easily calculate the fragments. Let's say, for example, the total fragment size is 4000 bytes, and the one fragment we can deliver only of 1400 bytes. So we have to divide this 4000 bytes into 3 parts: 1400, 1400, 2800, 2800 plus 1200. Okay. So this is the first fragment, this is the second fragment, and this is the third fragment. First fragment start from 00002 to 1399. Second fragment start from 14002 to 2799, and the last fragment start from 28002 to 3999. So the size of this fragment is 1400, the size of this fragment again in 1400, and the size of this fragment is 1200. What is the offset? Offset is calculated as the starting number of this fragment divided by 8. So 0000 divided by 8 is equals to 0. In the similar way, 1400 divided by 8 is equal to 175, and 2800 divided by 8, it is 350. Now, another thing is that if the data during the transmission of data, somehow the bandwidth is become low, so the communication media or communication line has to divide the one fragment to various subparts. Like for example, this is the same example. This is the original datagram. 4020 bytes kept for the HLAN header length. So the total size is 4020. This is the total length of this fragment, where 4000 is the size. 4000 is the size of this total data, and 20 is for header. When we are breaking it into 3 parts, so this total size is 1400, 1400, 1200, and 20 bytes kept carried from the HLAN. The total size of this datagram, fragment 1 datagram, is 1420. This is the total length, and the starting number is 000, 175, 350. This comes from this 0, 175, and 350. Okay. Now, the second fragment can be again fragmented into various sub-fragments. So, if the size of this fragment is 800, the maximum fragment size can be 800 in this question. So, 1400 is the size of this fragment, 800 and 600 is the 1400, 20 for the HLAN. So, 800 and 600. So, the sequence number is, the byte start from 14002 to 2199 and 2200 to 2799. So, what is the fragment offset? Fragment offset is always 1400 divided by 8 is 175 and 2200 divided by 8 it is 275. So this is the offset of first fragment, this is the offset of second, this is the offset of third, and this is the offset of the last fragment. Okay. So the questions on these fragment offset and the three bits used for the do not fragment and more fragments are as: a packet has arrived with a m bit value as 0. Is this the first fragment or the last fragment or the middle fragment? M, more bit, is 0. So it is not the, there is no more fragment. It means this is the last one. But is this is the first one? We cannot say. Okay. So these type of question we have already discussed in the previous lecture. So comes on next question. This question already discussed in the previous class. Okay, this is already discussed. This is already discussed. Now, the next question. The IP datagram has a field of checksum. 16-bit section is called checksum. What is the function of checksum? Checksum is used to detect and correct the errors. Basically used to detect the error. If there is some error, then we need to take some appropriate action. Like if 1-bit error, then it can be corrected. If more than 1-bit error, or you can say burst error, then the frame should be retransmitted again from the sender side. Okay. So how can we calculate this field? Like for example, this is the example of checksum. This is the IPv4 header datagram. This is the version field. This is the HLAN. This is the services. This is the total length. This is the fragmentation, and this is the first 3-bit that is 0 and do not fragment and more fragment. This is the fragmentation, fragment offset. This is the time to live, and so on. This is the source IP and this is the destination IP. So how can we calculate the checksum? To calculate the checksum is a 16-bit long. Okay. So we have to write it as 4500. This is a 4-bit, and this is 8-bit. This is a 4-bit, this is a 8-bit, and this is a 16-bit. So we have to divide this part in this way. So these are the 16-bit, 450. So we can write it 4500 because this 0 is 00. Again 28. 28 is the hexadecimal code. So we have to convert it into 28 is the not hexadecimal. 28 is the in decimal number. So we have to convert it into hexadecimal code. So 28 is equals to 0010. This is the hex code of 28. Similarly, this is again the 16-bit field, which has only the value of 1. So 1 can be written as 0001 and so on, 00 and so on. Again 10, 12, 14, 15. So we have to convert 10 and 12 separately, like 10 and 12. You have to convert 10 separately and 12 separately. 10 is written as A, it means 0A. 12 is written as C, it means 0C. So we can write it 0A, 0C. Keep in mind that decimal, you need to convert separately, 10 separately and 12 separately in this way. Also 14.45, yes, you can do it in the same way. 12.6, 7.9 in the same way. Now, you need to calculate the sum. When you are calculating the sum for E4, 4, 7, you are calculating the sum. This is the basic question. You need to calculate the sum of the hex digits. Okay. So how can we calculate the checksum? To calculate the checksum, this is the sum 744E. This is the sum, and you need to subtract from F. You need to subtract from this. So what is F? F is the 15. 15 minus E is 1. 15 minus 4 is 11. And you can write 11 as B. 15 minus 4 is 11. Again, it is B. 15 minus 7 is 8. So what is the answer? 8, B, B, 1. So this is the answer, and this is the checksum for this. So in the question of checksum, what is the code word and what is the data word? Data word is the what data we are sending, and the code word is the checksum. This is the code word. We have to send it. Again, at the receiver side, when this sum and checksum, or you can say the data along with its checksum is calculated as a sum, when you are totaling this, then the answer will become F, 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 F. Now calculate E plus 1, 14 plus 1, 15, 4 plus B, B is 11 and 4, 15, 11 plus 4, 15, 7, 8, 15, and for F, 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 F. So, if at the receiver end side, the sum of data word and code word is F, 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 then the data has no error. Otherwise, the data contains some error. Okay. So, now calculate this question. This is a very important question, and most of the examinations, in competitive examination, in AKGEC examination, in interview questions, this type of question is very common and can be asked everywhere. So, an IPv4 datagram has arrived with the following information in a header. Let's say this is the header now. This is the header. This is the version field. This is the HLN field. This is the total length field. So, we can write it in this way. This is the representation of hexadecimal. It means 45000054 and so on. This hex digit can be found, can be read from the packet, from the Wireshark tool. When you are using Wireshark simulator on your computer and opening a website, then you can check that this type of against IPv4, this type of data is transmitting from this node to this node and so on. So, this is the observation that the question is, the IPv4 datagram is this. Now, you need to calculate each and everything. What is the version of it? This version of this is 4. So, it is IPv4 datagram. HLN 5. So, what is the size of HLN? 5 multiply 4, it is a 20. HLN is 20. That's why, because this particular string is related to IPv4 and the HLN is minimum 20 bytes. So, this is not the corrupted frame. This is the correct frame. So, is the packet corrupted? Why? The packet is not corrupted because this is the IPv4 header format and the minimum data length of HLN should be 20, which is there. So, this is not the corrupted frame. Next, these 2-bit, 448, yes, these bit can be treated as the services. So, 00, it means default services. We are using default services. The services can be distinguished by DTRC. First 3 bit unused, last bit unused, and rest middle 4 bits is used. DTRC. D for minimize delay, T for maximize the throughput, R for maximize reliability, and C for minimize cost. If it is 0, then we are using default services. The next 54, 0054. This is for total length. Total length. Keep in mind that we are doing in this way. 4, 4, this is 8, and this is a 16-bit. Okay, the 16-bit is treated as the total length. So, this is the total length, 0054. So, 0054 is the 0054. How can we calculate it? You need to convert it into decimal number. So, 4 into 16 to the power 0 plus 5 into 16 to the power 1, and these are the 0. So, what is this? 16 5 is 80 plus 4. It means 84. Packet is corrupted? No, the packet is not corrupted. Packet is not corrupted because HLN is equals to, what is the size of option field? Option field size can be calculated as the size of HLN minus 20. So, HLN size is all in this question is 20 minus 20. So, HLN size is 20 minus 20. So, option size is 0. There is no option. What is the size of data? 84. 84 is the size of total length, and the data size can be calculated. Data size can be calculated as 84 minus HLN. HLN is 20. So it means 64 bytes. 64 bytes of data we are having along with this frame. Okay. How many routers the packet travels to? Now leave this question. Just read this. 54 again 00 00 03 58 and so on. So in this is the 16 bit byte, 16 bits used for fragmentation. So 0003, then 58 is what? This and this. So you need to 5850 for, sorry, this field 5850. Now calculate each and everything. 5 can be written as 0101. 8 is written as 1000. Okay. 5 is written as 0101 and then 0000. So first 3 bit is this 010, where we can read that this is a do not fragment. It means this is the last packet. We can calculate it is in this way. This is the last packet. And what about the other? Other is the fragment offset like. Okay. Next is 20. The next field is, this is 4 bit. 4 bit? 8 bit. 20. Next is 20. So you can calculate this is the time to live. This is the time to live 20. 20. What does it mean? 20. How many routers? 20. Time to live. You can calculate is in this 2 into 16 to the power 1 plus 0 into 16 to the power 0 is equals to 32. So 32 hops, or you can say 32 routers need to pass to deliver your data from this point to this point. Okay. And this particular thing, time to live, is always reduced, always a decrement as we have passed some routers. When it reaches to its destination, this time to live size is become 0. Okay. Next is this is 17. So next is 00 field. Checksum is this one. These are the source address and this is the destination address. So what is the source IP address? Source IP address is 7C4E0302. Destination IP address B40E0F02. You can convert it into decimal representation. You have already studied about its hexadecimal IP address into decimal notation of IP representation. Okay. So now comes on next IPv6. IPv6. IPv4 is a 32-bit address, while IPv6 is a 128 bits address. 128 bit. What is the need of IPv6? The need of IPv6 is that if we are using 32-bit address in IPv4, so somehow it can be as the number of computers are increasing. So at any time it may become shorter. So we need to increase the length of this IP. And some more feature also added to the IPv6. We will discuss it also. Basically, IPv4 is very good protocol, and we are working on it. Presently, we are using IPv4, but as a testing phase, IPv6 is auto implemented in our system. When you are checking your mobile configuration network setting or in laptop network setting, you are always seeing that IPv4, you can convert it or you can change it. In the similar way, IPv6 is automatically configured. You can manage it, you can customize it, but it is already configured just because of it is in testing phase, whether it is fully completed or fully there is any chance of improvement or not. Okay. So IPv4 has some deficiency. What type of deficiency? We will discuss this later. So IPv6 datagram. Okay. IPv6 datagram. The main important thing is that IPv4 also carries 65,530 bytes of data. IPv6 also carried 65,535 of data. base header is 40 bytes, while the base header in IPv4 is 20 bytes. This is the basic difference. So this is called the extension header, or you can say optional. Extension header is what? Extension header is that when you are delivering a large packet. So the large packet can be fragmented into various sub-fragments. In IPv4, each and every fragment has all the header and trailers, all the options, all the frame format functions in one IPv4 datagram can be carried with the fragment itself. All the separate. You have already seen that if we are using IPv4, then this particular frame data is this, but this frame is again and again can be drawn, or this complete data has been carried with the data. The size of data is 1200 bytes, size of data is 500 bytes, anything. So this is the basic problem. So if you are streaming a video, when you are playing a video and video size is too large, is the HD video. So when you are making a small fragments of HD video, so it is very tough to manage that each and every fragment of this video can be placed along with the IPv4 datagram. So there is some buffering is there. But while you are using IPv6, it is already finished. Buffering is not available because it do not carry the whole fragment, the whole format size along with the data. So this is called extension header. That's why this extension header is used. Okay. So this is the IPv6 header format. Like version field is same, is kept as the same. This is the priority bits. This is the flow label. This is the payload length, hop limit, next header, source and destination. This is small. Only this is. While in IPv4 there are several fields are there. There is only version, priority, flow label, payload length, next header, hop limit, source address and destination address. If there are multiple fragments are there, then this next header redirect it to the next. So next header and header length, next header, header length, next header, header length. Continuous data. Okay. So this is the way we can deliver the data in the continuous way. Okay. So next header comes for IPv6. How? If the next header code is 0, the hop by hop option. If the code is 2, then ICMP protocol is used. 6 is a TCP, 17 is UDP, 43 is source routing, and so on. This is the content of next header code in IPv6. Okay. The priority of congestion control traffic. Also, this one, this field priority. What is this priority? This priority is basically used when any packet is delivering from source to destination. There is some priority. If this priority field is 0, then there is no specific traffic, there is no congestion. We are assuming that this data is free flowing and there is no observation, or no observation is like that our data is delaying due to some reason. We are transferring the data. One is background data. When we are delivering the data as a background data, what is background data? Background data you can understand in this way. Like for example, if I am speaking you and you are listening my voice, but along with my voice, there is some background noise is there. There is a fan voice. Listen na, fan voice. So this is a background voice. Suppose I am listening. So this is the background voice. My voice is there, but along with my voice, another voice is there, which is not important, which is the intensity of that voice is very low. So this background voice can be eliminated during the transmission, during the delivering of the data. It can be removed. But if you are removing, then the data transmission is lossy data. Okay. So the observation is that you can deliver the data, but if you are using the background data is a special case. Background data, you need to deliver the background data also. Then this bit should be kept as a 1. Okay. Next is unattended data traffic. Unattended data traffic, which is not, which is waste, which has no use. So this type of data is called unattended data traffic. Reserve bit, attended bulk data traffic. we need to attend bulk data traffic. There is more and more fragments are there. This is also reserved. Interactive traffic means when we are conversation with other one. So there is two-way communication. So this is called interactive traffic. Control traffic, when we are controlling the traffic, that this type of data, this size of data we are delivering, this size of data we are not delivering. Okay. There are some more priorities are there. Data with greatest redundancy, data with least redundancy. If the priority bit is 1, so greatest redundancy is there. Multiple data is there. When it is 15, there is no redundancy. The data is completely unique. Okay. This is the comparison. The header length field is eliminated in IPv6, but it is available in IPv4. The service field is eliminated in IPv6. In IPv4, service field is there, but the priority and flow label field is kept in IPv6. The total field in IPv6 is replaced by payload field. This is the same. Total length and payload field is the same. The identification, flag, offset field are eliminated because base header in eliminated in IPv6. They are included in fragment extension header. The time to live field can be called here is hop limit, because in IPv4 also time to live we are saying that hop limit, how many routers need to pass, or what is the hop limit. The protocol field is replaced by the next field. The header checksum is eliminated because checksum is provided by the upper layer and the below layer also. So there is no need to provide checksum at this level. The option field is IPv4 is implemented as the extension header in IPv6. So these are the some important concepts. This is the extension header types: hop by hop option, source routing, fragmentation, authentication, encrypted security payload, destination options. There are various header types options are there. Okay. Comparison. The no operation and end of operation in IPv4 is replaced by pad1 and pad-n option in IPv6. The record route option is not implemented in IPv6 because it is not used in IPv4. The time stamping option is not implemented because it was not used. The source route option is called the source route extension header. The fragment field of the base header section in IPv4 has been moved to the fragmentation extension header in IPv6. The authentication header is a new in IPv6. The encrypted security payload extension header is new in IPv6. So IPv6 has very few more fields as compared to IPv4 features. Okay. So now the transition from IPv4 to IPv6. Currently we are using IPv4 and we are going towards the IPv6. So we have to make sure that how this IPv4 is converted to IPv6. In today's scenario also, some system is exclusively using IPv4 and some system using both the IP versions, and some system, only few systems are using IPv6 only, just for testing purpose. So how can we ensure that our data is still transmitted to other IPv4 to IPv6? There are different transition strategies are there: dual stack, tunneling, and header translation. So first we will understand what is dual stack. Dual stack. This is IPv4, this is IPv6. What this is dual stack? We are using this. This is a transport and application layer. These are the physical and data link layer. We are keeping both protocol at the same level. Both at same level. I am using IPv4 along with IPv6. You can say that in my network settings, in my computer network setting, both protocols are configured. Both protocols are configured. At the same level, at the destination point, both protocols are configured. So this is a dual stack. We are keeping both protocol IPv4 and IPv6 in our system. This is called a dual stack. Okay. Next is tunneling. Tunneling is what? Basically, you can understand tunneling in a very easy example. Like there are 100 people are going from one city to another city. Okay. The source address of these 100 people is different and the destination address of these 100 people is also different. But they are traveling through a bus or train. So during the from this place to this place, they are moving in a bus only. Okay. So when the bus or train start from this node to this node, the source and destination address of all the 100 people will become same. So this is the concept of tunneling. Like in a tunneling, if there is a IPv4 host or IPv6 host, there is a IPv6 host and this is IPv6 host, but the network using IPv4 region. So in IPv4 region, there is a router, So from this router to this router, a tunnel is there. Tunnel is called all the IPv6 packets kept together along with IPv4. IPv4 header is kept above and this IPv6 and payload is traveled from this node to this node and then IPv4 is stuck and IPv6 to deliver to v6 host. So this is a tunneling concept. And what is header translation? Is just the translating the header from one to just converting IPv4 to IPv6. IPv4 header, IPv6 header. Just remove the unnecessarily or the field which is not required in IPv6 and include the features which are used in IPv6, just converting. Okay. So this is a header translation strategy. So this is the some differences that IPv6 mapped addresses changed to the IPv4 addresses. The value for IPv6 priority field is discarded. The type of service field in IPv4 set is 0. The checksum is IPv4 calculated and inserted in corresponding field. There is some header translation strategies, procedure. How we are transferring from IPv4 header format to IPv6 format. The field which are not used in IPv6 are kept as a 0. Like for example, service field is not there, so we are skipping as 0. Checksum is not there, so as inserted in the corresponding field, calculating inserting corresponding field, it means in the next transport layer. Okay. IPv6 flow level is ignored because IPv4 do not have any type of flow level. So when we are converting IPv4 to v6, the flow level is ignored. Okay, like in this way. So these are the references from these books. You can study it in detail. So this is all about IPv4 and IPv6 header formats. So in the next lecture, we will discuss about some cryptographic concept, RSA algorithm, DES algorithm, Diffie-Hellman algorithm. So that's all for today. Thank you very much.